Question 5 is about the settlement of the underlying soil due to the applied load. And we have the schematic drawing of the foundation and the soils like this. This is the raft footing, which is embedded at 2.5 meters below the ground surface. And we have a layer of sand and a deeply buried layer of silted clay. So due to the applied load, the increase of the effective vertical stress throughout the clay is a nonlinear distribution as shown by the dashed lines. We can denote the increase of the effective stress at the top of the clay layer to be delta sigma top, T, and delta sigma at the middle, delta sigma M, and delta sigma bottom. So before we can go to the settlement, we need to figure out the increase of the effective stress, those three delta sigmas. As you have learned from CV 381, this delta sigma is determined by the delta sigma applied times the influence factor, and the influence factor is determined by the dimensions of the footing, the depth of the point, and the position of the point. And this delta sigma applied is equal to the total vertical load applied to the footing, P, divided by the area of the footing, minus delta sigma relieved by the excavation. So after we have this delta sigma applied and this influence factors find per the three different points required in this question as follows. The 3 points requested to figure out is the point at a corner. Let's say it's point A. The point at the center, which is point O, and a point at the middle of a long side, let's say it's point P. This influence factor can be found like for point A, like at the corner. Of this entire raft footing, which is let's say the dimension is 25 by 15. And for point P, we can divide this footing into two identical squares or rectangles. Let's say the point P is at corner. Of this rectangle, whose dimension is 15 by 12.5. And then we multiply the calculated delta sigma by 2. And for point O, we can furtherly divide this raft foundation into 4 identical rectangles. So we can say it's at corner of this rectangle with the 7.5 by 12.5 meters of dimensions. So this is 0.0, and then we multiply the calculated delta sigma by 4, then we get the increased vertical effective stress at this three points in the clay layer. Okay, after we find all of this delta sigmas for point A, delta sigma top, delta sigma at the middle of the layer, and delta sigma at the bottom, then we can find the average delta sigma under point A to be, since the distribution of this delta sigmas over depth is nonlinear, we can use this equation to calculate the average delta sigma for point A equals 6 under delta sigma top plus 4 times delta sigma middle plus delta sigma bottom. Similarly, we can find delta sigma average for point P and delta sigma average for point O. Then for the immediate deformation, which means elastic deformation immediately after the foundation is installed, we can use Hooke's law to find immediate settlement. Simply, we can use the equation as delta sigma average divided by the undrained Young's modulus or elastic modulus of the soil, undrained, as given in this question, and multiply this by the total thickness of the layer. Then you'll get the immediate settlement at under the point A, P, or O. And 2, for time-dependent deformation, let's say delta S, because it's related to consolidation, so we can find out the permanent settlement first, delta SP, which is equal to delta sigma average times MV times the thickness of the layer. And for the settlement at a given time, we need to find the time factor first using the given time. T equals CV times T divided by HDR square. Then we can use the time factor to find the degree of consolidation U, and then we can find the time-dependent settlement, say delta ST equals the permanent settlement times U in percent divided by 100. So for this three points, we can find 3 different delta sigma T, which means the settlement of the silted clay layer under these 3 points at any given time. Then you can draw a chart which shows the time dependent settlement for 3 points. Say point A, point O, point P. This three curves scratch here doesn't necessarily show the real relative position of these three curves you're gonna get. So you can use the Excel file to give a timeline of t equals 0, 2.5, 0.5, and until like 100 years or 50 years, just as whatever you like. And then you can get a chart to show the deformation of the soil at a given time. Then you can find the differential settlement between all these 3 points. 3 S is the design or dimensions of the footing.